Hello and welcome back to Calculus 3, section 11.7 on motion in space. So, we did this already. Its position is given by the vector r of t, which is set of parametric equations, which gives us the line in space. You can do the two-equation parametric set for 2D, or three equations for 3D, and four for 4D space, and so on. So, the path, the path is given by the vector-valued function, which is the set of parametric equations, and that is going to be f of t, g of t, and h of t, which gives us some kind of the path in our xyz space. So vector r points to a location at t equals some value. We know that this vector v will trace every single position starting from at the beginning of the trip all the way to the end of the trip if the t is finite, right? And if the t is infinite, then the path is infinite in length. Now we are going to apply to this r, we are going to apply our previous section with the calculus. We're going to take derivative of r, so get r prime of t, and that is clearly the velocity. So velocity is the derivative of the position, and that will be given as f prime of t, g prime of t, and h prime of t. So those are our velocity. And then we have acceleration a of t, which is the first derivative of the velocity, velocity vector, guys, which is the second derivative of position, which is f double prime of t, g double prime of t, and h double prime of t. There is another derivative for jerk, which is the third derivative of position. You experience it every time when you slam either on your gas pedal or your brakes, because both of those pedals are acceleration. And rapid change of acceleration produces jerk, which is why your face hits the steering wheel or your back of the head hits your seat, depending on whether you're accelerating or braking. So the change in position is velocity, the change of velocity is acceleration, and the change of acceleration is jerk, and that is where we stop. Now, we don't deal with the jerk in these lectures, so I'm just going to leave it there, but you should see it in physics at least. Yes?
Is A also a vector? Is that for something?
Yes, it is.
Okay.
Acceleration vector. All of these guys are going to have their direction. So, we did talk briefly and we touched upon, I'm not sure why this book is not talking about directional cosines. There is a way to find the direction in 3D space. Maybe I should actually make a copy of that and assign it at least to the honors students to look at it. I had a student last night from my Calc 1 class who is designing a 3D printer and needed to learn how to deal with the 3D space with something that some kind of conversion between the two systems, I had to pull up a different book that I have in my office to show the directional cosines, so that that can be programmed in so that the 3D printer can work properly. So all three of these vectors will have the direction. It's just that we don't deal with the direction in this book at all. They also have magnitude. The magnitude of the position vector will give you the displacement, not the distance, but the displacement. You have to be very careful with the distance and displacement because they are not the same thing. See, distance is how much you cover in time in a linear fashion. So your odometer on a car measures the distance because that's all of the path that you covered, where the displacement cares about the initial and final terminal position. So your displacement for a day, which is bed, whatever bed, right? You understand what I'm saying? Bed, whatever bed. So you go to a hike, or you go to school, or you go shopping, or whatever you do in a day, you come back home and you go back to bed to sleep the next night, right? Your displacement is 0 because you went bed RVCC bed, right? But your distance is bed 10 miles this way, 10 miles back, bed, so distance is 20 miles and displacement is 0. They are not the same concept. Be very careful. And if you studied physics, you know that those are not the same concept. So our position is going to be the distance covered. And if they're talking about displacement, just be careful because it might not be the same. You cover the distance when you go to vacation, so you get up in the morning from your bed and then you, I don't know, fly out at 3,000 miles and then you go to a different bed at night. Then you cover 3,000 miles of distance and displacement at the same time. So now they're the same, right? So the magnitude for the position is going to be the distance covered, and magnitude for velocity is speed. Very good. So off of this one, we have speed to be magnitude of velocity, which we know is this. So we have f prime squared plus g prime squared plus h prime squared. These are all functions of t. So you have your velocity, your speed. Guys, velocity is vector, which means it has the magnitude, which is called speed, and it has the direction, which you have to use directional cosines for. Now, it makes sense to have the speed limit on the highway rather than velocity limit because you want to go with the flow of traffic, right? So direction is implied, right? Otherwise, you are going to ruin your day and possibly someone else's day as well. So we keep the speed limit because we only worry about the magnitude of that vector. We all know that we should be going with the flow. So that's our initial talk. And now with this, if I give you, let's say, a helix, say we have r of t to be sine t, 2t, and cosine t. I will ask you to think a little bit about it and tell me which way the graph goes, because you are supposed to know this. And then let's calculate the velocity vector, acceleration vector, and let's calculate the speed. And then we can calculate those at 2 seconds or 3 seconds or you know. Yes?
Is that supposed to say sine t by any chance?
Sine t, 2t, cosine t.
Yeah, okay.
Right, so sine 2t, cosine t.
Okay.
I flipped it as much as I could to see if you understand the helix, because helix is one of the easy ones that we can deal with. You don't want to take a look at the flight pattern of a fruit fly, because that's going to be a living nightmare. But the helix is nice and nicely behaving, so let's talk about that. Yeah, we'll find everything. Velocity vector, acceleration vector, speed, and then we'll take a look at calculations as well. So first, let's take a look at the graph. If I draw my 3D coordinate system, where do I wrap the helix? On y, very good. We wrap helix around y because y-axis has the linear term on it. That means that the y-coordinate will be progressing linearly and the xz plane will progress in a circular fashion, right? So the base for the helix is going to be in the xz plane and it's going to wrap around y. Perfect. So there it is. Now that we have this, we can go and find our velocity vector, v of t, which is the vector of derivatives. We are applying a previous section where we take the derivative of each one of these independently. So derivative of sine t is, very good, cosine t. The derivative of 2t is 2, and the derivative of cosine t is negative sine t. Very good. Now we are going to find the acceleration vector, a of t. The derivative of cosine of t is, and derivative of 2 is, and the derivative of negative sine t is cosine t. Perfect. So we have these guys, and now we need to find the speed. Speed is going to be magnitude of the velocity, which is the square root of cosine squared t plus 2 squared plus sine squared t. Do we all agree that this is root 5? How much is sine squared plus cosine squared? 1 plus 4 is 5. Beautiful. So we have the speed to be root 5. Root 5 what? Apples? No, meters per second or feet per second or whatever, your miles per hour, whatever the units were for the distance and whatever unit of time we're using to measure all of this. So now, we know that speed is constant. Because it's just root 5. That's awesome. Right? We have a constant speed. Now, wouldn't that mean, if you have a constant speed, that acceleration is 0? Right? Look. In the y direction, acceleration is 0. Because you did have a linear rise. So, these things are something that you have to connect to your physics. Right? Constant speed means no change in acceleration. Just go back to your Calculus 1 and realize that acceleration is the derivative of velocity. And what is the derivative? It's the change, right? So if the speed is constant, that means that its derivative is not changing. That means acceleration is 0. No change means 0, right? So hopefully all of these concepts can, click and connect and make sense. So now I can ask, what is... Now, but you will say, but hold on, if I find the magnitude, that's a different thing. You have to be careful because... well, let's work out the vectors. So let's find all of these for time, let's say pi over 2, right? Seconds or whatever. So time is pi over 2 seconds. So what is my position? So position is going to be r of pi over 2. And if position is pi over 2, then we have our vector to be, what did I say? Sine was first, right? Sine pi over 2. And then 2 times pi over 2. And then cosine of pi over 2. So my r of pi over 2 is going to be 1, pi, and 0. What is this? This is location. Your vector will stretch from 0, 0 to the point 1, pi, 0. And that is location where your bug is, the fly, that it's flying in this helical path, right? You will go to 1, pi, 0, and that's where you're going to find your fly. So r points to the position in space. The terminal point of that vector, which stretches at 0, 0, to the terminal point. The terminal point is the position, the location where the bug is. Then you have your velocity. Now this is a velocity vector at pi over 2. We know that our velocity was cosine and then 2, so we have cosine of pi over 2. We have 2, and then we have sine of pi over 2. No, negative sine of pi over 2. So velocity vector is going to be cosine of pi over 2 is 0. This is 2. And negative sine pi over 2 is negative 1. Now, this is a vector. What is this vector? Well, guys, this is a tangential vector to the path. So, if... let me explain what this vector is. As you can see, you know that speed is root 5, right? So you see that these guys have right? I mean, obviously you see that the magnitude of this is root 5, because 2 squared is 4, plus 1 is 5, root 5 when you do the magnitude. But note that the velocity also has the direction. So what is this velocity vector showing? The easiest is to explain this using the 2D rather than the 3D. I can do it with 3D as well, but actually I'll do it with 3D. Just let me talk about 2D first. So if you have a circular motion and you have an object which is moving in this circular path, and the object, well, first off, to have circular motion, you have to have some force that pulls the motion inwards. For planetary motion, that is the gravity of a very massive object, right? Earth revolves around Sun because Sun is massive in comparison to Earth. Moon revolves around the Sun, Moon revolves around the Earth because Earth is far more massive than the Moon. So it's the force of gravity that pulls the object inwards. The velocity of the object is tangential. The object wants to just shoot straight, right? But the acceleration of gravity pulls and bends this vector, so at any point, right, all of these guys like this, and then it stays in orbit. Now, if you erase the Earth and you erase as soon as you erase the Earth, you erase this inward pull, which is actually going to be the A vector like this. The moon would just shoot straight tangentially. So the moon will just lose all of this and would just shoot that way. The only reason for the orbit is because there is a massive object in the middle that pulls inwards. So every single location is tangential, but it bends it so it has to. Now this is a crude picture. Obviously the gravity is distortion of the time-space, and then it bends the space, but that's completely different level. It suffices to explain this. Now, if you watched enough movies and you've seen those primitive weapons, everyone knows what's going to happen when I let go. And you are not at ease right now, right? Because this end over here is heavy, right? And because this end is heavy, as long as I let go, there is tension in this string. Tension is pulling towards my finger, right? If I let go, that tension is gone, this is free to go. Now, if you're trying to use this as a weapon, right, that the ninjas, get out around your ankles and then make you fall, right? Where do they have to let go, right, in a practice? Now, it's all in wrist, right? You know exactly where the object is because you are the one who's twisting it. If you want this to go straight, do you let go when it's here? No. Where it's going to go if I let go at this point? Exactly that way. Because the velocity vector is 90 degrees to this thing that way, right? It's difficult for me to do this and let go now, not because I care that I'm going to hit someone. I don't care about that. I care about the fact that it's moving too fast, you won't see it, right? So I would actually have to record that with a slow-mo camera, right? And then when I let go, you will see no matter where I let go, it will always be whatever the position of this was, 90 degrees in the consistent with the orientation, right? So I'm going to shoot now to go behind me. There you go. That's because I'm a ninja, but that's fine, right? So you get the idea. Anywhere you let go, it's going to go 90 degrees. So now, if you look at this vector here has the direction to it, and direction is 90 degrees to the position. And you can think about the orbit or these primitive weapons that were used. And also you can think about the car slipping on oil and leaves combination over here will continue tangentially, right? Even though the road bends. So that's something that, it's called tangential motion. Yes?
So the line that's 90 degrees from the position is the velocity.
Yes, because your position, when you are in a curved motion, your position is coming from the vector r, which is anchored at 0, 0, 0 somewhere, right? Okay. So your tangential vector is 90 degrees to it. Okay. And if you're talking about 2D space, your r vector will be pointing this way, your acceleration vector will be pointing inwards. And there's your gravity for planetary motion. Yes?
So would the direction of your velocity vector be orthogonal to the position vector?
Always. They're always orthogonal. And acceleration will always be orthogonal to the velocity. So, now that we are hopefully understanding this to some degree, we take a look at our acceleration at pi over 2, and acceleration at pi over 2 will be, what do we have? Negative sine, negative cosine. So negative sine pi over 2, 0, negative cosine pi over 2, which gives us negative 1, 0, and another 0. And that's acceleration. Now this is acceleration vector, right? So acceleration. So we have position, velocity, we know speed from before. Now, let's just exercise the demon over here and say, how about velocity at pi over 3? Why do I want to calculate that? Now, let's see. So what's cosine of pi over 3? And then 2, and then negative sine of pi over 3. So how much is cosine of pi over 3? Cosine of pi over 3 is? 1/2, very good. And 2. And then sine of pi over 3 is? Yes. Negative root 3 over 2. Perfect. We would agree that velocity vector at pi over 2 and velocity vector at pi over 3 are very different. We all see that, right? What's the magnitude of the velocity vector? Root 5. Without calculating root 5. You don't believe me? Oh, ye of little faith. Let's go. Absolute V is square root of 1/2 squared plus 2 squared plus negative root 3/2 squared. That's square root of 1/4 plus 4 plus 3/4, which is square root of, the middle one is going to be 16 over 4, 20 over 4 is root 5. You cannot escape that. You have a constant speed of root 5, every single velocity vector at any instance in time must be such that its magnitude is root 5 because speed is 5. Right? There's a reason why these things work without exception. Right? There are no exceptions to the rule. Every single one. How many possible times can you come up with? Infinitely many, right? All of them will produce root 5 on a speed. In this example, right? Now, if I come up with a helix that it's not linear in rise, then your acceleration will also be a function, and it will depend on how far into the motion, right, we are looking into, right? And then none of these things with a constant speed will hold, obviously. So don't study the example to memorize the example, because all of this goes to garbage as soon as I change the y, right? I picked the helix that it's not a standard helix. You are used to cosine, sine, and then t, because that is the basic helix of radius 1, rising linearly, speed 1 up. That's the most basic helix that you can have. What I decided is to actually wrap it around y by placing linear term in the middle. Another thing that I did is I flipped the orientation. Look, I have sine first. We know we're supposed to have cosine first, because then it's counterclockwise, which is the default motion, right? By me placing the sine first and then cosine, I have a clockwise orientation and clockwise progression as we go and wrap around y-axis. So, I drew it backwards. See that I have a backwards drawing? This is a counterclockwise drawing. Because if I'm to stand this up and put the clock on top, the clock actually does go this way. This is the counterclockwise. I need the clockwise, so I'm supposed to do this. I'm supposed to do that. Because now it's clockwise. So if you care, switch it around. It has to go clockwise as you. Now, whether you're going to stand up a clock here, right, in a background, you stand up a clock here, and you realize this is your 12 and 3 and 6 and 9. The clockwise direction would be this way, which is why I'm starting here, and it's going to go bend and go in a clockwise direction. Right? It has to go in clockwise because I put sine first. Now, counterclockwise is the default motion, but that calls for cosine first and then sine. Yes?
So this can work in 2D as well, right?
Yes, everything that I'm talking about can work in 2D, except you have to have 2 coordinates, right? Yeah. So the circle would just be cosine t sine t, unit circle, right? And all of this would work. Now, they worked out that example in a book, so I didn't want to bother you with a thing they already did. I will show the example, but and I know that all of you have the ability to read because you know the letters and numbers and things, but it's worthwhile talking about the diagram that is there. So your example in a textbook is a circle with radius 3, because you see that your r is given as 3 cosine t and 3 sine t. Having that, and you also see that it's one revolution of this circle because your t is from 0 to 2 pi, which is enough to trace only once. The black line here outlines the path function, and that is also, you can see it's counterclockwise because we have cosine first and then sine second. Now, observe that your red vectors are velocity vectors which are consistent with the orientation of the motion. Now you see that parametric equations are very powerful, right? Because you knew which way this rotates before you put any velocity vectors, right? Because of the orientation and the progression through the parametric equations. They're so powerful, really powerful things. So we have the consistency between the orientation of the function and also the velocity vectors. So now, the blue vectors are the ones that stretch to each point on the black line. Black line is the path. Blue line are the R vectors that stretch from the origin to trace the black line along the way. Red vectors are velocity, and they show which way the bug or whatever is on this path is moving. And finally, you have the orange vectors, which you may or may not see. Orange vectors are acceleration vectors, and they're the ones that are pointing inwards, making sure that these velocity vectors bend so this stays in the orbit motion. What do? As soon as you break that acceleration, the vector that bends this inwards disappears. That's me letting go. And the object flies off in the direction of the red, which is perpendicular to the blue position vector, right? Now you know why I wore this shirt. The tension in a cord as you are swinging, or the force of gravitational attraction, is the force that holds things together, holds them in orbit. As soon as you lose that force, you lose the acceleration term, and the mass has to fly off in the direction of the motion. Make sense? All of this is premeditated. Cool. So read example 1 is a two-dimensional example. I gave you a three-dimensional example with a helix. And then, think about these things and play with these things in your head to try and make sense of all of this. What else can we talk about? Straight line and circular motion. We can so here is the three-dimensional example. A path on a sphere. You have your sphere. So if you have a cosine and two sines, you're getting a slinky. When you have a sine and two cosines, you have a sphere. There is your a sphere and the black path, which is a circular path along the way. And you have an equation for the sphere, which is giving you the surface of the sphere. This thing over here gives you, just like, the eggshell, it's very, very thin, and then you have the inside, right? Or think of the basketball that has air inside, so, right? It's just that shell, just the outside. That is your surface, and you are moving on a surface. Just like we are standing on the surface of the planet. So this could be equator, and you can just walk straight and then swim and then walk and then swim, right? To go around the planet, walking on the equator. And you can calculate so that would be your path, and then you can calculate the velocity vector and acceleration vector just by taking derivatives. So we're not doing anything strange or weird, or just taking care of these things. Now, one thing that I find surprising is if I ask, give me the tangent line to the path, People freak out. Why do you freak out? You know that the tangent to the path is going to be your velocity. So if you have your velocity vector, isn't that the velocity vector that gives you the 3D slope of the line? That vector v in the equation that we had, so you had the vt plus r0. You should be answering that question like this if you understood the equation for a straight line. So going back to our example of the helix, if I want, and here I'll do it in red, because if I want the tangent line at t equals pi over 2, what is my equation of the line? My tangent line equation is going to be r equals vt plus r0. Guys, this is y equal mx plus b. Do you see that if you remember anything from your Calc 1, you should be remembering that your slope is the derivative. Isn't that the velocity derivative of r? It's the same. It's just, this is a multidimensional equation of this. This is a 2D, and this is NED. This works for 8-dimensional space. All I need to do is to have my vector have 8 dimensions. It's okay, right? So now, what do I know? I know that my velocity vector at pi over 2 is given as 0 to negative 1. I also know that my position, which is my r0 at pi over 2, is given as 1 pi 0. These are all things that I calculated earlier. Location at which there will be tangent line, the velocity at that point, which gives me the slope. So my r is going to be, my vector r, right, is going to be 0 to negative 1 times t plus 1 pi 0. What is my tangent line? It's x equals 1, y equals pi plus 2t, and z equals 0 minus t. This is the tangent line. Tangent line at t equals pi over 2. I got my direction, my slope for that tangent line because I have the velocity. I got my position to where to anchor my tangent line by calculating that point in space. And I just use the equation from the line in a vector form and just plug everything in. We calculated, here is the lines and things in space, there we go. And we go to the straight line, there it is. Your vector equation for the line. And your answer for the line has to be the set of 3 equations in parametric form, because the 3D line must be given as those 3 equations. So now when you go back to my answer, yeah, we had some zeros around, so it doesn't look exactly the same, but that's it. You have 3 equations as a parametric set for your tangent line in 3D space. You have to connect these dots, because this is how you build stuff and how you measure things, right? Guys, you have to understand that to shoot a rocket from Earth to Mars, you know what kind of shot that is, to just make it blind? The planet is rotating thousands miles per hour. At the same time goes around the sun. And the Mars is rotating, and the Mars is going around the sun. And then there is just so much space junk up there and satellites and things. You have to make sure you miss everything there. You don't slam into the moon. You also need to make sure that the planet is rotated right, and where you want to land on Mars is rotated right, and where the positions are relative to each other. And this all moves thousands and thousands. And we still shoot the object from the Earth as the Mars lander lands on the surface of the Mars and roams around. What do you think those calculations are? Yeah. It's this. So, keep track of velocity, keep track of acceleration, keep track of the relative position of the objects, and you can hit the target, right? Or you can just play basketball where you have an object that it's not moving, right? I dare these guys to play it so well if the hoops were rotating around the court, right? And now one side has a blue hoop, the other side has a red hoop, right? They can play in any direction they want. Let the hoops rotate. See how well that game is going to go and how much more practice they would have. That would actually be a good thing to design robots to do and see who has better programming and stuff like that. Here, I just gave you entrepreneurial idea to develop a new sport, right? It's like that and the soccer on the minefield. I would like to see that. Otherwise, I don't watch soccer. I would rather watch the grass grow. Or a football, same thing. Anyway, yeah, that's that, right? Do we have anything else we want to talk about? Yes. Two-dimensional motion in gravitational field. And it was so interesting to see how quickly the book washed their hands from the 3D one. Of course, because you don't have a position. You don't know the direction. You don't know where your stuff is. So you can't really develop 3D stuff because you don't teach directional cosines. So you see this wonderful explanation on 3 pages for 2D, and then the 3D half a page is like, okay, well, this is right. You can also do it in 3D, right? Oh, next lecture, 11.8. So, you know, if you want to work for SpaceX or NASA or whatever, you'll have to sit down and figure those things on your own. Motion, gravitational motion in 2D, I believe that's the, what's the exact title? Oh, 2D motion in gravitational field. So 2D motion in gravitational field. Interesting for them to mention the field before we get to chapter 14 to explain what the field is. Gravitational field, just like magnetic field or the wind or electric field or whatever other field, is going to be space filled with vectors, where every particle of that space is progressing according to the function that it has to obey. Now, for 2D motion, it suffices, because the planet is so big, for us to say that, you know, we draw a little flat piece here, and then we just draw the arrow down, and we say towards the center of the Earth, and that's your acceleration vector, which is actually your gravitational pull, given as 9.81 meters per second, or 32.2 feet, per second squared, sorry, or feet per second squared. And we put negative, yes?
Isn't it supposed to be 9.80 meters per second squared?
9.81, but actually there is a range. Okay. Depends on how high you are. The average is 981, 98.1 is the average that we would all use, but the range goes between the, what's the name of that trench where they buried the Decepticons? Mariana Trench, thank you. And the top of the Himalaya, right? Mountain, Mount Everest, there is a range of G, right? Which will be moving in those decimals. When we get lazy, we use 10, right? If you want to be as precise as you want to be, you use 9.81. 9.8 is just fine. So whatever you use, it won't kill your... So we have our flat platform. I'm not saying flat Earth. I'm not an imbecile. And we have our flat platform here because it does appear to be flat if you are zoomed in so much. Just like your cord. Does this look 3D to you? Does it? No, it's just one-dimensional length. You don't care that this has thickness, right? It's just a line. The ant walking on this, yeah, because it's so close and so small, right? And the ant to this, so the ant can work, right? You perceive this as one-dimensional because it is, the length is so much bigger than the width that you don't even care. Would you care about one piece of paper and say it's three-dimensional? Of course it is, but its thickness is so small that it's negligible, so you only care about the surface area of that paper, and you say, yeah, a piece of paper, it's like a rectangle. No, rectangle is two-dimensional object. But we let it slide because its third dimension is negligible in comparison to the other two dimensions. Just like the two dimensions of the intersection of this chord are negligible to the dimension of length. So when you say a flat piece, you don't mean flat Earth, you mean that the Earth is so big and you're so small that you can perceive as the flat piece. Now, if you shoot something into the air, it falls back on the Earth because of the gravity, right? Here. And it's always parabolic motion. Why is it parabolic motion? Well, because of math and differential equations. So now let's work it out. We are going to start with the concept of acceleration vector, which will have negative g on its y, and there will be no acceleration in x. When you drop something, it goes straight down. It goes down in the fashion to get to the center of the Earth the fastest, the fastest it can. You don't get to drop something and then it goes there and there and there. No, it goes straight down. Well, if you put the paper, obviously, but that's the drag, it's the air, it's, you know, all these things. But if you drop anything that is heavy where the air is not going to make a difference, right, it's just going to go straight down. So this is your acceleration. Acceleration vector is 0 for x motion, and y goes straight down at a negative g. Now we know that the acceleration is the change of velocity in time, and hello differential equation. This is a differential equation which shows that that you have the velocity, you have the time, and then you have a gravitational constant. This is 9.8 that you want. So now we do separation of variables, which is you put dt to the other side. So this is differential equation. Use separation of variables. Now, you learned this basic idea of separation of variables in your Calculus 2 course. There was a section on differential equations, I believe 7.9. And you learn a few basic ideas there. This is the one of them. So now when you separate your variables, you integrate both sides. The integral of dv is just going to give you vector v. And on the other side, you're going to have that you'll have constants, right? So integral of 0 is 0, but you will have a constant, let's say c1. And integral of negative g is negative gt. Right? What's the integral of negative 3? It's negative 3x, right? So integral of negative g must be negative gt, plus some constant c2. Every time you integrate indefinite integral, you better put plus c. Otherwise, I'll get allergic to you. And that allergy spreads rapidly. So now we have our velocity as a function in time. I just want to use the same letters as in the book. So this C1, they call in the book U0, and C2 they call V0. Negative GT plus V0. I have to box this equation because this is important equation. We'll come back later to explain physics of it, or just doing math now. Now, your velocity is the change in position in time. So now we have another differential equation on our hands. So this is again differential equation. We do separation of variable, leaving dr on the left and moving dt to the other side. And then we integrate both sides. So now, integral dr will just give us r of t. And on the other side, I have integral of u0 is a constant, right? So integral of a constant is going to be u0t plus c1 constant. And then I'm going to have the comma over here. And now I'm integrating negative gt. That's going to be negative g times t squared over 2. When you integrate t, you get t squared over 2, plus v0t plus c2 constant. Now, guys, this is position. Position is given as x and y. So now we're having our vector r of t given as u0t plus x0, comma, negative 1/2 gt squared plus v0t plus y0. And this is that other very important equation, and this ends mathematical calculations. Now we are supposed to make sense out of all of this. So let's look at it. First, I want you to realize that u0 and v0 are components of velocity, and x0 and y0 are components of position. So this is what we have. So what do I do now? let's draw an object which flew to the location from t equal t0 to t equal t1. So time has passed. And we are going to observe the experiment again in class as I toss this eraser. There's something better. Is this better? All right. Well, we'll do two experiments. Note the path that the object takes as you throw it. What kind of path do we have? It's a parabola, right? It's a downward opening parabola. Downward opening parabola. Do we see downward opening parabola? We know that the downward opening parabola is negative x squared. Well, now we are on the time axis, so sure. I have negative t squared, and I see that in my equation. And where do I see that in my equation? On the y-axis, on the y-coordinate. Now, when I throw this, your height changes as a parabola. But you only have a progression forward. Note that there is no parabola going forward. Going forward, you have linear. Right? So, as you are looking at these equations, right? As you are looking at these equations, you have the progression moving forward in x direction, and you have object goes up and down parabolically for y. Now, what is important when you are looking at these equations? Gravity. Gravity is acceleration which pulls downwards. It's bad words, but no, fine. It's different for different size of objects. The gravity of the moon is different than the one from the Mars, is different than the one from the Earth. For Mars, we have issue with the atmosphere. We have the issue with the soil that is rich in the minerals that are poisonous to us. You cannot go and grow trees on Mars because the ground in Mars doesn't have the same chemical structure as the Earth. And it's full of minerals that are highly poisonous to us. The atmosphere is also overrich with nitrogen. There's no oxygen. Terraforming of Mars will take forever, right? But we can make enclosed habitats and live in those because the Mars is not as bad as we think. What is the issue of Mars? Gravity. Weaker gravity at 2/3. What does it mean? You can jump higher. But what does it mean for the people that are born there and live their entire life, and how do they evolve in time? Different bone structure, different bone density, and if they come to Earth, they will not be strong enough. You would be able to flick anyone and kill if they were born on Mars and come here, because the gravity is lesser over there. So, anything that flies through the air, anywhere it is, gravity is an important factor, and that's the one that it makes sure that the things come back with a negative in front. Initial velocity. There is a difference in doing this and this. The only difference between these two throws was that V0 there. It has the angle at which you launch, and it also has how strong you're hit. As a kid, I used to play a game, and just the other day I've seen a commercial within a cell phone game, little tanks, and I used to also play worms. You pick the angle at which you want to throw projectile, and then some games have also depending on how long you press the fire button, it will launch at the higher power or lower power. Whatever you are adjusting there, you're adjusting the angle and the magnitude at which you are shooting, right? You program that in a video game like this. That's your V0. And finally, you have your Y0. Why are all basketball players 73 feet tall? Right? Why? Because the taller you are, you get to shoot from the higher distance, the further away the ball goes. It's very simple. If you're a short person, you don't get to play basketball professionally. Right? Now you can go and cry about inequality, but your genes. Right? So these are things that are all important, right, to consider as you are creating a projectile. Now, whether you are tossing something to your friend or you're launching a missile, right, this is the equation that equally governs both of those situations. Because we just derived it using differential equations, starting with the fact that when you drop something, negative g is going to slam it to the earth. Now, why does it slam it? Because of the force. This part over here is your negative g. If something exists in a physical realm, it has mass. Mass is the quantification of physical existence. So mass times the acceleration creates the force, and the force slams the object into the ground, right? So we have the gravity with the acceleration. And eventually we derive the equation for the motion. So this is your path. If you differentiate this, you will get your velocity. If you hit that with the absolute value, you will get the speed of the object that you threw. And then if you take another derivative, you're just going to end up with 0 and negative g, because that's what the parabolic motion has. Does this cover propulsion? No. No. Because propulsion is going to use the fuel to add extra force, and this doesn't hold. Your acceleration in a car doesn't come from gravity, unless someone picks you up and then drops you, right, with a crane. Then it's this. Your acceleration in a car is made by exploding dead plants and animals in your engine, and then you go forward, right? That's our technology still. Over 100 years old, and we still have people that are, I mean, I have to understand it, because we still have people that go, horses! Really? I have this most beautiful horse. I say, my car, which is a piece of garbage, because it runs on fuel, right, has 221 of your horses. So there you go, right? It's like, oh, but my horse is, you know, whatever. Electric cars. That's our next step in evolution. 98% efficiency. Our gas-powered car, 27% efficient. That's how sad we are as a species. We think we're cool because we have cell phones. No. No. We're not cool. All right. Two-dimensional motion. How do you calculate the maximum height? What happens at the maximum height? Toss this up. Velocity 0 at the top, exactly. So all you need to do is to go to your velocity equation, and you make sure that your y-coordinate is equal to 0. You will calculate the time at which you know your initial vector because you launched it, and you know the gravity, and it has to equal to 0, so you will be able to calculate the time at which max height happens. As soon as you have the time, you go to position, you plug that time into position, and you know where your object is. The y-coordinate will tell you where, right? What's the highest altitude that it reaches. So when they do those stunts, right, they actually compute these things, because you don't eyeball it and say, yeah, we're going to clear the bus. No. You actually compute this because you know the weight of the person that you're launching from the cannon, you know the distance, you know everything, and then you calculate the times, you just make sure it's going to clear the bus. Otherwise, right, you might not have the next volunteer to go into the cannon and be launched for the, right, if this person just makes a pancake into the side of the bus. That's it. See you Friday in the other room.